Now we'll go a little bit more in depth on how to draw a conclusion in a hypothesis test using a level of significance and a p-value. Like we said, usually the significance level or the level of significance is going to be 0.05 or 5%, but once in a while we make it smaller, like 0.01 or 1% or something else, depending on the situation. For example, the same example we saw the previous page, white male support for Obama. Let's return to the hypothesis test about white male support for Obama. The null hypothesis was the proportion of white males voting for Obama in 2012 is 0.40, and that was based on what we said. We thought it was probably about the same as what was in 2008, which we knew. But the alternative hypothesis said the proportion of white males voting for Obama in 2012 is less than 0.40. Now let's suppose that our random sample of 200 white male voters has 35% planning to vote for Obama in 2012. Just like we saw on the previous page, clearly 35% is less than 40%, but is this difference statistically significant, or is it just due to chance? We saw on the previous page that the probability, the p-value, was about 0.078. What can we conclude? A small p-value indicates that the data are unlikely to occur in random sampling from a population in which the null hypothesis is true. So the smaller the p-value, the stronger the evidence against the null hypothesis. Do you view something that happens 7.8% of the time as highly unlikely? Depends. I'd say at least unlikely, but maybe not highly unlikely. It's a judgment call. There's no right or wrong answer. Because this is a judgment call, we will often agree to a definition of highly unlikely, quote unquote, before we run the test. This is the significance level, alpha. This significance level is a benchmark for how small the p-value must be in order for us to say results are statistically significant. It gives us a cutoff point for rejecting the null hypothesis. Here are the decision-making rules that we gave earlier. First, if the p-value is less than or equal to alpha, we reject the null hypothesis in favor of the alternative hypothesis. Or if the p-value is greater than alpha, we fail to reject the null hypothesis. Why do these rules make sense? Visualizing a simulation of the sampling distribution is helpful in understanding these rules. So here's what we look at here. On the left, we see a graph that shows alpha being 5%, okay? The vertical bar here, the blue bar, is 5%. It looks like more of our data values are outside that bar when alpha is 5%, but if alpha is 10%, then the vertical bar at 10 contains all of our red values. So on the left, the conclusion is the data is not statistically significant because there's still some chance, these red ones that are to the right of the vertical bar, that the null hypothesis could still be true because it's possible that this would happen. But here, all the data values in red are smaller than that alpha. So the chances of it happening are not great. The data is statistically significant. It's rare in random sampling if H sub 0 is true. So you'd probably reject the null hypothesis here. Here would fail to reject the null hypothesis. Keep in mind that all the sample proportions in the simulation did actually occur when we selected random samples from a population with p equals 0.4. Results less than 0.4 support the alternative hypothesis, but to varying degrees. To provide enough evidence to reject the null hypothesis and accept the alternative hypothesis, results have to be smaller than 0.40 and highly unlikely. When we set the significance level at 5%, in other words, alpha is 0.05, we agree to view the results that occur less than 5% of the time as highly unlikely when sampling from the population described by the null. In this case, the observed sample deviates enough from the hypothesized population proportion that we reject the null hypothesis and accept the alternative. If we set the significance level at 10%, for example, alpha is 0.10, we've changed the definition of highly unlikely. If alpha is 0.10 or 10%, then we're saying anytime we get a p-value that's smaller than that, even 9% or 0.9, then we're going to reject the null hypothesis. As you can see from the simulation above, different significance levels can lead to different conclusions. Here are our conclusions for the two different levels of significance. At 5%, our poll results are not statistically significant because our p-value is 0.078, which is 7.8%, larger than 5%. We conclude that white male support for Obama will not be less than 40% in 2012. Note that this statement says we do not have enough evidence to accept the alternative hypothesis because the alternative hypothesis is related to the claim or hunch that motivated our investigation. We state our conclusion in terms of the null hypothesis. At the 10% level, our poll results are statistically significant. The p-value is 0.078. We conclude that white male support for Obama will be less than 40% in 2012. Note that this statement says that we do have enough evidence to accept the alternative hypothesis. Again, the conclusion is stated in terms of the null hypothesis. So how do you choose a significance level or the level of significance? Remember that the purpose of the hypothesis test is to describe the degree of evidence that a sample provides against the null hypothesis. The p-value does this. How small a p-value is convincing evidence. It depends on the situation and the opinion of the people who use the hypothesis test to make the decision. If rejecting the null hypothesis will be controversial or expensive, then the users of the test result may want to use a smaller level of significance than we did. For this reason, we always report the p-value with our conclusions so that the people who use the results of the test can determine if the p-value is strong enough evidence for their purpose. Later, we'll discuss other considerations for choosing a significance level.